Welcome to the Amazon Recognition demonstration. Amazon Recognition is a managed machine learning service you can use to analyze images and video. The service is easy to use. You just provide an image or video, and the service can identify objects, people, text, scenes, and activities. It can detect if there is any inappropriate content as well. Amazon Recognition provides highly accurate facial analysis and facial recognition. You can interact with the service either through the AWS console or programmatically through the AWS CLI or API. Here we are on the Amazon Recognition page in the AWS console. As you can see, there are a few demonstrations built into the console with preloaded images. We're going to provide our own images, but you can always review the pre-built demonstrations by simply logging into the AWS console with your account. For our first demonstration, we will upload an image for object and scene detection. Within a few seconds, Recognition returns the results. You see that it has recognized that the image includes people and has associated the terms clothing, apparel, coat, and handrail with the image. For our next demonstration, we will upload an image of a woman sitting with a dog for facial analysis. The analysis creates a box around the face in the image. This box is known as a bounding box, as it creates a boundary for the analysis. Amazon Recognition has identified that this is the face of a woman, that she is between 26 and 40 years old, appears to be happy, is smiling, and wearing glasses. In this next demonstration, we will use facial comparison to see if Amazon Recognition can determine if two images are of the same person. I'll pick the same image we used for facial analysis. I will then pick another image of the same woman in a group. In just a few seconds, Amazon Recognition determines that there is a match and that it is 97.7% confident of that analysis. I will now demonstrate how Amazon Recognition can extract text from an image. Amazon Recognition picks out the text from the image and displays the two words Thanksgiving and happy. These are just a few examples of how you could use Amazon Recognition to analyze images. You can also analyze video to identify individuals, objects, and scenes. You can even pick out celebrities from videos. You can find a good demonstration of that built right into the Amazon Recognition console, but we're going to upload a short video for demonstration purposes. Amazon Recognition has identified 14 unique individuals in the video. You can select Show More to see the faces of all of the individuals. In addition, Recognition has identified 39 objects and activities. You can select the Objects and Activities tile to see a list of those. You have now seen how to work with Amazon Recognition through the AWS console. Most real-world applications of Recognition interact with the service through either the AWS CLI or the API. This concludes the Amazon Recognition demonstration. You can get more information about Amazon Recognition from the aws.amazon.com/recognition homepage. Thanks for watching.
In this section, we'll look at preparing custom datasets for computer vision so you can detect custom objects. One challenge of using a pre-built model is that it will only find images it was trained to find. Though Amazon Recognition was trained with tens of millions of images, it can't detect objects that it wasn't trained on. For example, consider the 8 of Hearts playing card. If you run this card through Amazon Recognition, the results show various attributes. However, none of the labels are playing card or 8 of Hearts. If you want Amazon Recognition to detect images in your problem domain, you must train the model with your images. So in this section, you'll learn how to train Amazon Recognition with images from your problem domain. Though you'll focus only on using Amazon Recognition here, you'll encounter a similar process if you use other pre-trained models. Training a computer vision algorithm to recognize images requires a large input data set, which isn't practical for most organizations. Many machine learning problems today can be solved by training existing models, or you can use a managed service like Amazon Recognition Custom Labels. Like other machine learning processes, you need to train Amazon Recognition so it recognizes scenes and objects that are in a specific domain. You'll need both a training dataset and a test dataset that contain labeled images. If you have images that need labels, you can use Amazon Recognition Custom Labels to simplify your labeling tasks. For example, it provides a UI for labeling images, which includes a feature you can use to draw bounding boxes around images. It can also help find objects and scenes that are unique to your business needs. You can use it to classify images or detect objects within an image. Say you want to identify specific machine parts in images, such as turbochargers or torque converters. You could collect pictures of each kind of machine part and use them to train your model. Amazon Recognition Custom Labels also includes automated machine learning capabilities that handle the machine learning process for you. When you provide training images, the service can automatically load and inspect the data, select the correct machine learning algorithms, train a model, and provide model performance metrics. When you finish training your model, you can then evaluate your custom model's performance on your test set. Each image in the test set has a side-by-side comparison of the model's prediction versus the label it assigned. There are also detailed performance metrics for you to review. You can start using your model immediately for image analysis, or you can iterate and retrain new versions with more images to refine the model. After you start using your model, you can track your predictions, correct any mistakes, and use the feedback data to retrain new model versions and improve their performance. So how do you label images? The diagram shows a typical process for training a computer vision model, which includes the Amazon Recognition Custom Labels feature. We'll step through this in some detail. The process of developing a custom model to analyze images requires time, expertise, and resources. It often takes months to complete. It can also require thousands or tens of thousands of hand-labeled images so the model has enough data to make accurate decisions. It can take months to generate and gather this data, and it can require large teams of labelers to prepare it for use in machine learning. Amazon Recognition Custom Labels builds on the existing capabilities of Amazon Recognition, which is already trained on tens of millions of images across many categories. Instead of thousands of images, you can upload a small set of training images that are specific to your use case. Typically, you'd use a few hundred images for this. You can use the AWS Management Console to upload training images. If your images are already labeled, Amazon Recognition Custom Labels can begin training your model. If they're not, you can label the images directly in the labeling interface. Or you can use Amazon SageMaker Ground Truth to label them for you. There'll be more on that shortly. Amazon Recognition Custom Labels works best when you use different models for different domains. For example, if you need to detect both machine parts and plant health, you'd use two different models. Images you select for training should be similar to the images that will be used for inference. Use images that use various lighting conditions, backgrounds, and resolutions. Ideally, your training images will mirror images you'd want to perform detection on. If you can use the same source, like you'd use in production, that works best. The documentation includes additional guidelines on image type, so whether they are JPEGs or PNGs, and other properties like image size and resolution. That's it for part 1 of this section. We'll see you again for part 2, where we'll review how to create the training dataset. Hi, welcome back. We'll continue exploring video analysis by reviewing how to create the training dataset. Datasets contain information that's needed to train and test an Amazon Recognition Custom Labels model, such as images, labels, and bounding boxes. You can use images from Amazon S3, or you can upload them from your computer to S3 as part of the process. To train a model, your dataset should have at least 2 labels, with at least 10 images per label. Each image in your dataset must be labeled. As we mentioned earlier, you can use the Amazon Recognition Custom Labels console or Amazon SageMaker Ground Truth to label your images. Again, to train an Amazon Recognition Custom Labels model, your images must be labeled. A label indicates that an image contains an object, scene, or concept. As we mentioned earlier, a dataset needs at least 2 defined labels. Also, each image must have at least 1 assigned label that identifies the object, scene, or concept in the image. When you apply labels to an image as a whole, these labels are known as image-level labels. They're useful for identifying scenes or concepts that you want to detect. For example, one of the images shows a beach scene from Ko-Olina. It's on the island of Oahu in the US state of Hawaii. To train a model to detect beaches, you'd add a beach label that applies to the entire image. You can also apply labels to specific areas of an image that contain an object you want to detect. For example, if you want your model to detect Amazon Echo devices, it must identify the different types of Echo devices in an image. The model needs information about where the devices are located in the image, and it needs a corresponding label that identifies the type of the device. This information is known as localization information. The location of the device is expressed as a bounding box. The example objects with bounding boxes image shows a bounding box that surrounds an Amazon Echo Dot. The image also contains an Amazon Echo without a bounding box. The output of the labeling process will be a manifest file. The manifest file for an image-level label typically contains the label, or class name, along with some metadata about how the image was labeled. For object detection, the manifest contains information about each labeled image. The bounding box identifies where the object is in the image, along with the label that the bounding box belongs to. We've mentioned Amazon SageMaker Ground Truth a few times. We'll now look at what it is and how it might help you. With SageMaker Ground Truth, you can build high-quality training datasets for your machine learning models. To use it, create a dataset that needs labeling. You then provide detailed instructions on what needs to be labeled and submit the job. You can decide who processes the images to create a labeled dataset. You can use workers from the Amazon Mechanical Turk service, a vendor company, or an internal workforce with machine learning. You can use the labeled dataset output from SageMaker Ground Truth to train your own models, or you can also use it with Amazon Rekognition custom labels. SageMaker Ground Truth can use active learning to automate the labeling of your input data. Active learning is a machine learning technique that identifies data that should be labeled by your workers. In SageMaker Ground Truth, this functionality is called automated data labeling. Automated data labeling can reduce the time and cost it takes to label your dataset, compared to using only human workers. When you use automated labeling, you incur Amazon SageMaker training and inference costs. Yes, we just said that you can use machine learning to label the images that you'll then use for machine learning. We'll talk through how this works. When SageMaker Ground Truth starts an automated data labeling job, it selects a random sample of input data, or objects, and sends it to human workers. When the labeled data is returned, SageMaker Ground Truth uses this data, which is the validation data, to validate the models that were trained for automated data labeling. SageMaker Ground Truth runs a batch transform job using the validated model for inference on the validation data. Batch inference produces a confidence score and quality metric for each object in the validation data. Automated labeling determines if the confidence score for each object, which was produced in step 5, meets the required threshold, which was determined in step 4. If the confidence score meets the threshold, the expected quality of automatic labeling exceeds the requested level of accuracy. The object is then considered to be automatically labeled. Step 6 produces a dataset of unlabeled data with confidence scores. SageMaker Ground Truth selects data points with low confidence scores from this dataset and sends them to human workers for additional labeling. SageMaker Ground Truth then uses the existing human labeled data and the additional human labeled data to train a new model. The process is repeated until the dataset is fully labeled, or until another stopping condition is met. For example, automatic labeling can stop when you meet your budget for human annotation. We recommend using automated data labeling on large datasets. The minimum number of objects allowed for automated data labeling is 1,250. However, we strongly suggest providing a minimum of 5,000 objects. That's it for part 2 of this section. We'll see you again for part 3, where we'll review how to evaluate and improve your model. Hi, welcome back. We'll continue exploring video analysis by reviewing how to create the test dataset. The final step before you train your model is to identify a test dataset. You will use this test dataset to validate and evaluate the model's performance. You'll do this by performing an inference on the images in the test dataset. You'll then compare the results with the labeling information that's in the training dataset. You can create your own test dataset. Alternatively, you can use Amazon Rekognition custom labels to split your training dataset into 2 datasets by using an 80-20 split. This split means that 80% of the data is used for training and 20% is used for testing. After you define the training and test datasets, Amazon Rekognition custom labels can automatically train the model for you. The service automatically loads and inspects the data, selects the correct machine learning algorithms, trains a model, and provides model performance metrics. You're charged for the amount of time a model takes to train. A dataset that contains more images and labels will take longer to train. When training's complete, you evaluate the performance of the model. During testing, Amazon Recognition Custom Labels predicts if a test image contains a custom label. The confidence score is a value that quantifies the certainty of the model's prediction. Because this is a classification problem, the results can be mapped to a confusion matrix. With a true positive, the model correctly predicts the presence of the custom label in the test image. That is, the predicted label is also a ground truth label for that image. For example, Amazon Recognition Custom Labels correctly returns a cat label when a cat is present in an image. For a false positive, the model incorrectly predicts the presence of a custom label in a test image. That is, the predicted label isn't a ground truth label for the image. For example, Amazon Recognition Custom Labels returns a cat label, but there's no cat label in the ground truth for that image. For a false negative, the model doesn't predict that a custom label is present in the image, but the ground truth for that image includes this label. For example, Amazon Recognition Custom Labels doesn't return a cat custom label for an image that contains a cat. With a true negative, the model correctly predicts that a custom label isn't present in the test image. For example, Amazon Recognition Custom Labels doesn't return a cat label for an image that doesn't contain a cat. The console provides access to true positive, false positive, and false negative values for each image in your test dataset. These prediction results are used to calculate the various metrics for each label and an aggregate of metrics for your entire test set. The same definitions apply to predictions that the model makes at the bounding box level. With bounding boxes, all metrics are calculated over each bounding box in each test image, regardless of whether the boxes are prediction or ground truth. To help you, Amazon Recognition Custom Labels provides various metrics. For example, you can view summary metrics and evaluation metrics for each label. It also provides precision metrics for each label and an average precision metric for the entire test dataset. Precision is the proportion of positive results that were correctly classified. Amazon Recognition Custom Labels provides average recall metrics for each label and an average recall metric for the entire test dataset. Recall is the fraction of your test set labels that were correctly classified. Using the previous example of cats, that would be how many cats were correctly classified. The service also provides an average model performance score for each label and an average model performance score for the entire test dataset. The F1 score combines precision and recall together to give you just one number that quantifies the overall performance of a particular machine learning algorithm. You might use the F1 score when you have a class imbalance, but you also want to preserve the equality between precision and sensitivity. A higher value means better model performance for both recall and precision. If you're satisfied with the accuracy of your model, you can start using it. That's it for part 3 of this section. We'll see you again for part 4, where we'll review how to evaluate and improve your model. Hi, welcome back. We'll continue exploring video analysis by reviewing how to evaluate and improve your model. In general, you can improve the quality of your model with larger quantities of better quality data. Use training images that clearly show the object or scene, and don't include many things that you're not interested in. For bounding boxes around objects, use training images that show the object as fully visible and not hidden by other objects. Make sure that your training and test datasets match the type of images that you'll eventually run inference on. For objects where you have just a few training examples, like logos, you should provide bounding boxes around the logo in your test images. These images represent the scenarios you want to localize the object in. Reducing false positives often results in better precision. To reduce false positives, first, check if increasing the confidence threshold enables you to keep the correct predictions while eliminating false positives. Increasing the confidence threshold eventually results in diminishing gains because of the trade-off between precision and recall for a given model. Next, check to see if you need to add additional classes for training. For example, if you are detecting cats, but often dogs are being flagged as cats, add dog as a label to your training dataset, along with the images of dogs that you got the false positive on. Effectively, you're helping the model learn to predict dog and not cat through the new training images. You might find that the model is confused between two of your custom labels, cat and dog. The test image with label cat is predicted as having labeled dog and vice versa. In this case, first check for mislabeled images in your training and test sets. Also, adding more training images that reflect this confusion will help a retrained model learn to better discriminate between cat and dog. Reducing false negatives often results in better recall. To reduce false negatives, first lower the confidence threshold. This should improve recall. Also, use better examples to model the variety of both the object and the images they appear in. Finally, split your label into two classes that are easier to learn. For example, instead of good cookies and bad cookies, you might want good cookies, burnt cookies, and broken cookies to help the model learn each unique concept better. If you're satisfied with the performance of your model, you can make it available for use by starting it from the console or by using code. After the model is running, you can perform an inference with the AWS CLI or the SDK. When you call the API, you specify the Amazon resource name of the Amazon Recognition Custom Labels model that you want to use. The Amazon resource name is also known as an ARN. You'll also specify the image you want the model to make a prediction with. You can provide an input image as an image byte array of base 64 encoded image bytes, or as an S3 object. Custom labels are returned in an array of custom label objects. Each custom label represents a single object, scene, or concept that's found in the image. A custom label includes a label for the object, scene, or concept that was found in the image. It also includes a bounding box for objects that were found in the image. The bounding box coordinates show where the object is located on the source image. The coordinate values are a ratio of the overall image size. Finally, the custom label includes the confidence score. This represents how confident Amazon Recognition Custom Labels is in the accuracy of the label and bounding box. During training, a model calculates a threshold value that determines if a prediction for a label is true. By default, the detect custom labels operation doesn't return labels with a confidence value that's less than the model's calculated threshold value. To filter the returned labels, specify a value for min confidence that's greater than the model's calculated threshold. You can get the model's calculated threshold from the model's training results in the Amazon Recognition Custom Labels console. To get all the labels regardless of confidence, specify a min confidence value of 0. If you find that the confidence values returned by the detect custom labels operation are too low, consider retraining the model. You can restrict the number of custom labels that are returned from the detect custom labels operation by specifying the max results input parameter. The returned results are sorted from the highest confidence to the lowest confidence. Here are some key takeaways from this section of the module. Models must be trained for the specific domain that you want to analyze. If you're looking for turbochargers, you'll need many pictures of turbochargers to train your model. You can set custom labeling for the specific business case. We looked at the custom labeling process and some of the tools you can use. If you want objects to be detected, you need to label images and create bounding boxes for these objects. You can